Okay, so today we have a related rates problem from the Calculus Chapter 4 notes, and I've already drawn the diagram, and I'm going to explain each and every bit of information as we go through it, as always. And it says a balloon rising from the ground at 140 feet per minute. So let's think about a balloon rising above the ground. So I have my ground denoted by x, and the balloon rising above the ground denoted by y. So we can think about the balloon changing with respect to time. Well, the balloon rising above the ground with respect to time at 140 feet per minute. Okay, and they say it's tracked by a rangefinder at point A. So here's my point A, located 500 feet from the point of liftoff. So if this is my point of liftoff and this is my rangefinder, my x distance is going to be 500. And they want the rates at which the angle at A and the range are changing when the balloon is 500 feet above the ground. So they want how the angle is changing with respect to time when our balloon is 500 feet above the ground. So this is what we want. Okay, so the first thing is that I want to relate an angle, and I have an x value, and also I know that I'm going to be taking the derivative of something. So if I want to take the derivative of something, it's going to be y, because if I take the derivative with respect to time, I'm going to end up with a dy by dt. So I know that the three things I want to relate is theta, x, and y. So I'm gonna say equal to, and I'm gonna say, okay, I want y on the top and 500 on the bottom. And I'm gonna explain why I did this after we take the derivative. So if I think about y over 500, I'm going to think about opposite over adjacent, and that's going to be tangent theta. Okay, let's take the derivative of both sides with respect to time. So d by dt of tangent theta is equal to d by dt, and it's going to be y over 500. Okay, taking the derivative of the left hand side, the derivative of tangent is secant squared theta, and then by chain rule deriving theta with respect to time, I'm gonna have d theta over dt, and that's gonna be equal to. Now the reason I wanted y on the numerator is because if I take the derivative of this, I'm going to have to use the quotient rule. And the quotient rule always says that I'm going to have the bottom squared. So if I had y on the bottom, it's going to be y squared. And I don't really want y squared on the bottom, I want 500 squared on the bottom, which will be much more easier to simplify. So taking the derivative of y over 500 by quotient rule, I'm going to have the bottom multiplied by the derivative of the top. So that's going to be dy dt, and then minus the derivative of the bottom multiplied by the top, and that's just going to be 0, so I don't really need to write that. and this is going to be all over the bottom squared. Okay, so far so good. So we already have d theta dt, which is what we want, or one of the things that we want, and we have dy by dt, which is another thing that we wanted. So cool. In the next step, I'm gonna sub in, actually I'm not gonna sub in dy by dt just yet. Let's just write down the left hand side as is. And if we think about 500 squared, this is the same thing as 500 times 500. So if I have to rewrite this, I can cancel these out, and I'm gonna separate these two. So I'm gonna say this is 1 over 500 multiplied by dy by dt. So in the next step, I'm gonna sub in dy by dt, and I'm gonna divide both sides by secant squared to get my d theta dt alone on the left hand side. So let's do that. Let's say, okay, my d theta dt is gonna be alone on this side. So if I divide the right hand side by secant squared theta, it's going to be 1 over 500 multiplied by dy by dt is 140 feet, so we can say multiplied by 140. And we're going to divide both sides by secant squared, so we can say divided by secant squared theta. Okay, so let's think about secant squared theta. So secant of theta is just 1 over cos theta. That's by definition. So if we think about cos theta by SOHCAHTOA, that's going to be adjacent over my hypotenuse, and if I take the reciprocal of that, I can get, well, secant is r over 500. So let's sub that in. So that's going to be equal to 1 over, actually I'm going to write 140 over 500 divided by, and we said secant is r over 500 all squared. So now we have r as an unknown, and you might be thinking, what is r? How do we get r? Well, we do have a right angle triangle, so by Pythagoras I can say, well, r squared is equal to x squared plus y squared. This is by Pythagoras. So we know that x is 500, and we also know that we want d theta dt when y is 500. So we know that r squared is going to be equal to 500 squared plus another 500 squared, because again x is 500 and we want when the balloon is 500 feet above the ground, or in other words when y is a point of 500. So let's think about this, because I'm not just going to sub that in, that looks confusing. if I had x squared plus x squared, I can rewrite this as 2x squared. So what stops me from writing this as 2 into 500 all squared? Can you see that? That's the same as 2x squared. So now that looks better to sub in. So let's put my equal to in. Well, if remember this is just r squared. If I distribute this exponent into that, that's going to be the same thing as r squared over 500 squared by exponent laws. And we have an r squared. So I'm not going to take the root of both sides. Okay, we already have an r squared. So let's sub that in. So we have 140 all over 500 divided by 2 into 500 squared all over 500 squared. This cancels, and this is going to be 140 divided by 500. If I think about dividing this by 2, dividing by 2 is the same thing as multiplying by half. So if I multiply this by half, I get 140 on the numerator, and 500 times 2 is 1000. And writing this in terms of radians, I can say, well, the balloon is rising at 0.14 pi radians a minute, which is our d theta by dt. So they said find the rates at which the angle at A and the range R are changing when the balloon is 500 feet above the ground. Well, it's changing at 0.14 pi radians every minute.